Wait, so it's recording now, right?
Yeah.
Okay, so hi everyone. I'm Akshara and I'm going to be doing a quick crash course on 3501, which is water resource engineering. So if at any time you guys have questions, please let me know and I shall try to answer them. Basically how it's going to work is that I'm just going to give you a quick overview of the course structure, so basically what you guys will be learning over the 10 weeks. Then we'll delve into week 1 and 2 in a bit more detail with me. And then Johnny, he's going to come in and do weeks 3 and 4. And then at the end, there's going to be like a short quiz. It's pretty easy, it's about 10 questions. And that will be all. And then also all of these notes that you see on the board, I'll put on a Google Drive and upload and share for you guys. You good?
Yeah. I might dim the lights in front since it's a bit easier to see. Yeah. You just keep going.
So,
That should be fine.
can you guys see the board pretty well? Oh, not really.
Okay.
Okay. Maybe we'll like zoom in a bit. When I'm like trying to go through something, I'll zoom in quite well. So what I was saying before for those people that just walked in is that I'm gonna send you guys all of what you see on the screen. So feel free to take any notes if you guys want, but otherwise they're all gonna be available to you after this, right? Okay, so what you're looking at here is basically just an overview of the course from when I did it in 2022. 2023. Basically, when it was run that year, we were asked to come up with a formula sheet or formula sheets, 2 double-sided A4 sheets. So this is mine. And I just wanted to show you guys, just so that I can walk you through the overview. Don't worry about all the formulas that you see on the screen. Like, they'll walk through it with you, so you don't have to understand everything that's going on right now. This is just a very quick overview, just so that you guys get the structure, right? So the first bit of the course is this light blue section here, which we go through in week 1. And it's all about energy, water, and radiation balance. So you've got equations like Stefan-Boltzmann's law, Wien's law, and then radiation balance. And that's all about calculating like the amount of shortwave radiation, long-wave radiation from the sun and back from the atmosphere to the sun again, or into the atmosphere. There's also, so basically this diagram here is probably a better way to explain it. So without looking too much at the formulas, basically what it's about is that you've got the shortwave radiation coming from the sun and entering the atmosphere, and then the radiation is then reflected back from the surface. And you'll hear terms like albedo and emissivity, which is all about the amount of reflected light and radiation from the surface or the atmosphere.
Can I quickly add?
Yeah.
Akshara will send the notes over as well. So, like after the workshop. So if you ever feel like you missed anything or whatever.
There's absolutely no need to copy all of this down.
Yeah.
This is like a week, like 2 weeks worth of work that you're looking at from when I did it. So there's no way that I expect you to like copy it all down in like one session. So again, more radiation calculations down here. And yeah, that's all week 1. In my opinion, it's probably important for the assignment. You guys will have an assignment in week 1. Oh, sorry, not week 1, like week 5-ish. And I think it's important for that, but otherwise, they don't bring it up again in the rest of the course. The rest of the course starts here with hydrology, right? So the first thing that you'll learn is evaporation and evapotranspiration, which I'm going to go into in more detail, so I won't spend a lot of time talking about that right now. But you will also learn flood frequency analysis in weeks 3 and 4. You'll learn, let me find how to calculate rainfall. So using methods like the Thiessen method, for example, which is taking an area and kind of estimating it to give like an approximation of how much rainfall a certain area gets. And you can use that method as well for like evaporation to calculate how much water is evaporated from the surface into the atmosphere. Again, we're going to go through some of the terms for evaporation and evapotranspiration later on. Another thing that we will do, or that you guys will do, is flood frequency analysis. So you can have a quick read of these steps here. There are a couple of methods for flood frequency analysis that you guys will go into in a bit of detail. They're kind of relevant for, I believe, assignment 2, which happens around week 8. And finally, yep, this is all of this on the right here is flood frequency analysis. And then this final part here is about stream flow. So you'll look at like the shape of different water bodies, the depths, and also like the variation of depth as well. So I don't know if you saw this diagram before, but obviously the volume and the area will heavily determine the flow of water through a water body, which also plays quite a vital part in how likely it is for that water body to flood as well. But that's pretty much all there is to hydrology, and that will take place from weeks 2 to about 7. Week 8, we start to look at groundwater calculations. I won't go into too much detail about this, but basically you're just calculating flow based on like porosity and like the conservation of fluid, as well as the changes in pressure and depth. But you won't really need to know all of this until week 8, and you need to learn the hydrology part anyway, so you don't need to worry too much. Okay. Something to note as well, looking at all of these formulas, is that if you've done fluid mechanics already, you might recognize some of these formulas. So a good thing would be to kind of like revise that if you have completed that subject. Otherwise, does anyone have any questions before I get into the content? Okay. Okay, so I'm just going to start with the first part, which is week 1 over here, which is energy balance. So in the simplest of terms, when water goes from solid to liquid to then vapor, that whole process requires energy input. So a couple of terms that you will have to remember is like calorie, which is a unit of energy. So 1 calorie is required to increase 1 gram of water by 1 degree Celsius. Something to keep in mind when you're completing this course is the units. They're a bit of a pain sometimes, especially when you're expected to convert between like volume units and then also Celsius to Kelvin. There are quite a few formulas in this course that only take temperature in Celsius, but then others where you'll have to convert to Kelvin, which is just like to add the 273. Another important term is the latent heat of vaporization, which is basically the energy input required to evaporate water. Evaporation, which I'll go into a little bit more detail in like the coming slides, I guess, is basically just the movement of water from a water surface. So there has to be a water body there for evaporation to occur. And it's from the surface of that water body to the atmosphere. Okay. Yep. Oh, another thing about latent heat that you might want to take note of is that it's specific to water at 20 degrees Celsius, which you might want to take note of. And also the units are megajoules per kilogram. Okay. Any questions on that first concept there? Okay. The second part is not too difficult, so it's just the hydrological cycle. You guys, like in high school and even primary school, would have probably learned it, known as the water cycle, right? So basically, it's just a system where water moves from one body to the next. So as you can see there, the ocean body to the atmosphere, that's called evaporation. So you'll remember before when I said evaporation requires a water body. Basically what that means is that there has to be like a water body available there for it to be called evaporation. Otherwise, there's another term for it, but I'll get into that in a second. From atmosphere to land surface, we're calling it precipitation, which is where the water molecules that have been evaporated into the atmosphere cool down enough to return back from water vapor to the liquid state and go back to the land. And then land surface into the ocean is just called water runoff. So there's a diagram there that you might want to look at. It's a bit more complex than the diagram that I drew down there, but it's just another diagram. So there's the water body there where the evaporation goes when the particles in the water get enough kinetic energy to evaporate into the atmosphere. Once the moisture heads over the land and it becomes too cool to remain in the water vapor state, it then precipitates, and if it precipitates high enough, it will run down back into the ocean through either groundwater or through vegetation or through the ground surface. The next term, just an important term that you'll hear thrown around a lot in this course, is variability. So one thing that you'll hear a lot of is climate variability, mostly because Australia has a really high climate variability, which means that the climate is not very predictable, so it changes around quite a bit based on the temperatures, like the unpredictable temperatures that we have. As you can see here, another term that you'll hear is like human interference. So because we're constantly burning fossil fuels, there's a lot of industrialization, there's urbanization, we're kind of expediting the variability process. Okay. Like I mentioned before, part 3, I wanted to do a quick section on the units. So a couple of common ones that you'll see, well, mostly you'll use SI units, the units that you've probably used in like, all of your courses, but other ones, well, like common ones would be meters, kilograms, and seconds, and then the other ones that you might not have heard are amperes, which is like an energy of wavelength unit, Kelvin, which I mentioned before, was a temperature unit, the candela CD, which is the luminous intensity, so the amount of light that a water body is exposed to, or just the land surface. And then a mole is just another word to describe the amount of a substance in a system. So let's say you were determining the amount of like a certain chemical in a water body, you would use moles because they tend to be more convenient to use when you're working with like really small amounts of substances. If you're doing a lot of chemistry in the future, you'll hear that one thrown around a lot as well. Okay. Any questions so far? Right. Okay. So now this is kind of more what you'll be looking at in week 1. So the whole idea of atmospheric circulation is the imbalance in radiation. So imbalance in radiation causes the winds and the currents, which therefore influence the hydrological circle. So if you think about it, if you have a really high current or a really high wind, then it's all right. You might have like a different rate of flow of like, water runoff, or you might have a higher evaporation rate if there's really high temperatures and no wind at all, right? Just a quick common fact about the atmosphere. the composition of gases in the atmosphere is made up of 78% nitrogen and 21% oxygen, and then the 1% is just noble or inert gases, which I can kind of show you here. This is kind of taken from our notes from last year, which is like a very complex composition of the atmosphere table. You won't need to remember all of them, but it is useful to kind of remember the chemical formulas just because they might get thrown in like a question or something. So it's useful to know what they are. By the way, if I'm going too fast at any point, please let me know and ask any questions at all. Okay. So just a quick note on radiation. I mentioned before that about shortwave radiation and longwave radiation. So basically shortwave radiation is of solar origin, which means it comes from the sun and it enters our atmosphere. And then longwave radiation is the radiation that is reflected back from our surface to the atmosphere again. And the formula that we use to demonstrate this whole concept is called Stefan-Boltzmann law, and is used to determine the energy flux or energy flow from a body if the surface temperature of the body is known. So one important thing to know if you take anything away from that formula is that you have to have the temperature of your surface to use it. All right, so that's the formula there. You will know your T, basically. You're finding the energy flux. You will use the Stefan-Boltzmann constant, which you can kind of note down there. That is constant, that won't change. And then you have the emissivity light of surface, which will the range is usually 0 to 1, unless you're talking about a black body of water, which I'll go into more detail during the course, but it basically means that the emissivity is only 1. Right? Okay. So now I'm going to talk a bit about evaporation and evapotranspiration. So this is kind of an important concept that you guys will have to know for your assignments and exam questions. So we'll start at the very top here. This whole unit or this whole week is about water that is being removed from our surface, right? Whether it's water bodies or whether it's like the land surface, right? So there are two types. One is evaporation, and then the other, which I said I would mention before, is transpiration. So like I mentioned before, evaporation, the amount of water that passes into the atmosphere has to be from a water body. And then transpiration is when the water is removed from the vegetation, either just from the surface of the vegetation, or it could actually be through the stomata of the internal plant system, and that's how the water can escape as well, the moisture. And when we take those two terms and combine them, we get evapotranspiration, which is the combined process that includes all of the water leaving the surface of the earth and going into the atmosphere. Does that make sense, that whole concept? Great. All right. So there are other technical terms or evaporation types that will be thrown around during this course, and they're quite important for when you need to do evaporation calculations. Because basically, you can't measure the entire area of like Sydney, for example, or like even Australia. So what we do is that we estimate using a certain area, and we kind of use these terms to help us, right? So firstly, the ETO is the potential evaporation, which is the maximum amount of water evaporation, considering that the availability of water is non-limiting. So I don't know, can someone think of a water body where the availability of water is non-limiting? So there's no chance that it could dry out. Yeah, the ocean, right? So like a really open body of water. So yeah, maximum amount of water evaporated, and just remember like that blue part there is really important. So for you to consider the potential evaporation, the availability has to be non-limiting. Okay, so the actual evaporation, very similar, is just like if you're estimating in the same area, it's basically like the amount of evaporation that you actually measured. So not the maximum, but the like always equal or less than the potential evaporation, basically. Right? And then finally, the reference crop evaporation is kind of different. This one is measuring the rate of evapotranspiration. And with this one, it's quite important. There are always these assumed conditions. So if you want to note down anything from this, I would note down those. You have to consider the crop height. Crop height meaning, like, I guess maybe the density of the vegetation, like the depth of your vegetation, whether it's like a rainforest or like a wheat field, you know. There's obviously quite a large difference there, so the evaporation is going to differ quite a bit. Canopy resistance, the range of the crop height is from 0 to 12, has to be. The canopy resistance is always 70 seconds per meter. And then the albedo, which I mentioned before, was the light reflected by the surface, is always going to be 0.23. Make sense? Okay, moving on to the physics of evapotranspiration. Okay, so I kind of have a diagram here. I hope it makes sense. But basically just imagine that this is an open water body in step 1, and then you've got the atmosphere above, right? So imagine that nothing has happened yet, and then when you add the increase in temperature, the molecules in the open water body, they kind of are given more kinetic energy, or they gain more kinetic energy, and that allows them to like escape the water body into the atmosphere, right? And then in step 3, what happens is that some of those escaped water bodies cool down a bit. And then that allows them to enter the water, or they try to enter the water body again. So if they're going from water vapor to liquid, do we remember what that's called? The word for it begins with C. It sometimes happens on your like drink bottle. If you had a lot of ice in it, kind of like drops a bit.
Condensation.
Yes, that's it. Condensation, right? And then finally, in step 4, this is kind of the important part, what we're leading up to, is that there's a really thin layer in between the water surface and the atmosphere that is caused by the constant movement of water molecules from the water body to the atmosphere and vice versa, right? So once the water molecules escape this layer, so once they get past the saturated layer in like the light blue there, it creates more space for the evaporation from the surface. So that's how evaporation is continued, right? And now we get to an important formula called Dalton's law, which demonstrates that entire process that I just explained. So basically here we have 4 different components. E represents the evaporation. You have the coefficient of evaporation, which will most likely be given to you, or you'll have to find using the other components. And then you've got the 2 saturated vapor pressures. ES just represents like the general saturated vapor pressure. And then saturated vapor pressure at dew point is the saturated vapor pressure at which the temperature the dew point is at the temperature at which water condenses. So the difference will give you your amount of evaporation from the water surface to the atmosphere. Over here is kind of a carry-on from that. So more often than not, you will have to find the saturated vapor pressure in order to find your evaporation. So that's how they kind of make the exam questions like a little bit more difficult, but it's not too hard. Basically, all you have to remember is that the saturated vapor pressure is a function of the temperature. So as the temperature increases, so does the saturated vapor pressure. And this is one of those formulas where I've mentioned before, it's really annoying. It only works if you use the temperature in Celsius, and then the ES is in kPa. If you want to take note of that formula there. Okay. Other than that, there's not too much going on in week 2 other than this, which is just the evaporation measurement techniques. You'll learn a few more techniques than what I've mentioned here, so this won't be all of it, but basically the one that you need to be really familiar with is the Class 8 evaporation pan technique, because it's the most widely used, and it's used for measuring the potential evaporation, which, if we want a reminder, is this one here. So the maximum amount of water evaporated from a surface, considering the availability of the water, is non-limiting. Another thing to remember is that the dimensions of the Class A evaporation pan are fixed. So we have a diameter of 120.7 centimeters and a depth of 25 centimeters. And so basically, if you can picture it, is that they just stick the pan in the evaporation site, and then they take the evaporation or the change in water level, and they kind of use that to estimate like an enormous area or like the surrounding area evaporation, if that makes sense. But other than that, I'll just wrap it up quickly. Those two are just some extra formulas there for calculating the available energy, which is just considering like the outgoing heat conduction into the soil, the net incoming radiation, which would be like your shortwave radiation from the sun, and your latent heat energy, which is kind of considering the amount of energy required to evaporate the water. Yeah, that's it for week 2. I'll hand over to. Okay, so
You get assurance.
Because if I leave
okay. So just a quick review. So yeah, 1 calorie is required to increase 1 gram of water by 1 degree Celsius. So basically, just to review, I guess, to increase anything by or to increase the temperature of anything, you have to input energy. That's one way to remember it. So the units for energy, or at least in this course, would be calorie. That's the next question. Yeah, okay, cool. Everyone got that right. That's good. That's good. Okay, define the potential evaporation. So, I don't know, I was kind of mean with this one, to be honest. I kind of like, they're all the same answer, just with like 1 or 2 words changed. But the potential evaporation is the maximum amount of evaporation from a surface where the availability is non-limiting. So remember, that's like our open body of water, that's like our ocean, and then the potential evaporation is just the maximum amount of water that can be evaporated. Does everyone understand that now? Cool. Yeah, we got that right. We got that right. That's right. So this was the Class A evaporation pan. So that's the one that is most widely used in hydrology to measure the potential evaporation, or rather to estimate the potential evaporation of an area. So it's taking our like small pan with the dimensions and sticking it in an area and kind of using the change in water level to measure like how much evaporation can occur in that fixed area that you're measuring. Okay, so the ES is a function of temperature, I guess. So if it kind of helps, basically what this means is, so ES is the saturated vapor pressure, right? Do we get that? Okay, so saturated vapor pressure, when you think about it, warmer air can hold more water than cooler air. So the more the temperature rises, the greater the saturation level is going to be, if that makes sense. Yep, and then I think finally, so what does the EA represent? That was very similar to ES, but it's the saturation vapor pressure at dew point. And just as a recap, the dew point is the temperature at which the water is evaporated. Oh, hang on, let me review it. The water condenses. Sorry, the dew point is the temperature at which the water condenses, which is why you're finding the difference between the saturated vapor pressure and the saturated vapor pressure at dew point, because you just want the evaporation. You don't want anything that's coming back down to the surface. And I think that's it. That's all for weeks 1 and 2. Well, that's all I can cover.
Start talking. I love talking. I don't know if I'm in view. Okay, my name is Johnny. I did this course actually with Akshara and Henry last year. And best advice I can give you, like in a nutshell, or at least I'm sure all of you guys have already made these conclusions. I didn't. This subject was very confusing in my head because every week it was just like something else. That's probably because every class I was just wasting time and like talking and not paying attention until the very end when it was like, what does this subject mean? But basically, in a nutshell, this subject is just the water cycle but on drugs. Okay, it's just, that's it. It's just the water cycle with added steps. It's all about modeling and prediction of rainfall and storm events and how we can understand the changing flows in waterways as a result. Okay, so after week 4, that's when we start, or week 4 is when we start looking at the statistics behind flood events and rainfall events and the damage or basically the repercussion of that. So for example, once every 100 years we might have like a really big storm event, and so given that much rain, what will the flood look like? So there's a lot of statistical modeling around that. The maths for it isn't very difficult, but I'm not going to go into anything too number dense today. I do have one example question, but it's for something that's not very complicated. Has everyone done soils? Have you guys done soil mechanics? Okay, beautiful. That's what I like to see, because if you've done soils, this subject's not going to be too bad. There's a few soils topics that we go through.
But if you haven't done soils, it's also okay.
Yeah, it is also okay, yeah.
I didn't do soils when I did it, and I was fine.
Yeah, and Akshara like hit it out of the park. We walked into the exam and we had one cheat sheet. It was Akshara's cheat sheet, and we all like smashed the exam. It was so good. So, you know,
well,
I think
you guys are gonna get it. So
yeah, okay.
you can see for yourself.
But yeah, so make sure, like, make friends, have people to study with, because vocalizing the concepts and explaining it will help you visualize everything in a better way. Okay, so week 3. So this is when we start to look at the actual landscape and how water changes and flows as a result of the storm. So this is the actual actions of the water cycle. So first point is the hyetograph. Okay, and what a hyetograph is, it's the diagram, or it's like a graph which tells you the rainfall over time. So I didn't really put a diagram in there because I didn't really think it was important, but I'll just draw an example of what it should look like. So let's say this is our millimeters of rainfall, and this is our time. So storms are usually measured in periods. So let's say this period is going to be a 1 hour period storm. Okay, so this is 0 hours, 1 hour, 2 hours, 3 hours. 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters, 5. So in the first hour, let's say only like 1 millimeter on average fell across that hour. All right, the second one would probably be, let's say it's like 4, and then it builds up to 5, and then every hour after that it like decreases. Okay, so the reason why this is important is because as storms occur, it doesn't just across the whole hour, it's like 3 millimeters every hour and then it stops. It's like a gradual, like it builds and then it falls. Okay, so if you ask yourself what is the most logical explanation for what's happening, that's chances are is the correct explanation, because this subject is all about the real world. Okay, so if you in your head can imagine, okay, this would make sense in the real world, that's probably your best starting point to understanding what the question or like what's going on. Okay, so that's a hyetograph. A hydrograph is different. So a hydrograph is the amount of water that's flowing through a waterway over time. So if you look at the unit of measurement for a hyetograph, it's millimeters over time. The hydrograph is going to be meters cubed over time, right? Because it's the amount of volume of water flowing through a waterway. Okay, so how I'm going to explain this. So if we look at the hydrograph, right? The flow within the waterway reaches a peak. And this is after all the rainfall has already occurred. So the storm is going to appear in this part of the timeline. Okay? And then all the water is going to drain from the catchment into the waterway. And usually when the rain has stopped, that's when the water will be, the flow will be at its peak. Okay? Because it's going to start falling. Why? Because there's no more water being fed into the waterway. Does that make sense? Okay. You can actually draw the hyetograph and the hydrograph together. So let's say this is my time. This is my, okay. We'll say this is my millimeters and this is my volume. So the blue line is going to be my hyetograph. Okay, so let's say in the first hour we got, I don't know, 2 millimeters. In the second hour we got like 6. And then the third, okay, that's probably too fat. Whatever, let's just break it up a bit. So this is our rainfall in millimeters, right? So the first hour probably would have been 2, this is 4, 6, 4, 2, and then 1, I don't know. Doesn't need to be accurate. As a result, this is how the flow within the waterway is going to change. So since this is where the rainfall stopped, this is probably where our peak is going to be. Now, that is not entirely 100% always the case. There are a lot of factors that change how this shape is, and I'll get into that in a second. But this is what it's probably going to look like. Okay. So the peak is going to be where the rainfall kind of stops. Does that make sense? Okay. Let's keep going. So. Okay, so this is basically just explaining like the different, like analyzing the chart itself. So like time to peak and then time base. Why is this still there? Okay, so base flow. Let's actually talk about the base flow. So the reason why I rubbed this out and I kept it like that, can someone explain to me what this level is? So if this is talking about the volume within a waterway, what's that measurement there? Where it starts stable and then ends stable. What's that? Okay, so let's say it's not raining. You walk past a creek. Okay, I won't say creek. Let's say a river. You look into the river. Is there water in the river? Okay, so that stable level of flow throughout the river, chances are always going to be the same. That's your base flow. So that's the water level where it starts and it ends. Now it's not always the same. Like, do you see how my line's kind of diagonal? Like it's meant to change a little bit afterwards. That's the base flow. So this one is like, when we get to the calculations, I'll talk more about why that's important later. But basically that's that. Time to peak, so that's how long it takes for the peak to occur, so the biggest amount of water to be flowing through the river at one time. And that's important because you want to know when the flood's going to occur. All right, so next bit. So this diagram's kind of like what I drew before. Actually, no, that is that. Right? It's just something that's a little bit more accurate and less sort of simplified. Okay, what are the important concepts I wrote? So the duration is very different to the duration of the hydrograph. So yeah, duration of rainfall. So that's, as I mentioned before, so the time that the storm occurs is different to the time it takes for the flood to occur and then to recede. Hydrograph is asymmetric, as you can tell, because it takes a lot longer for it to drain than it does for it to fill up. Okay, I wouldn't really worry about the last point because that is the excess rainfall. Okay, that's just like a mathsy thing. Okay, I think from here this is a good time to explain what a catchment is. Do we know what a catchment is? Okay, cool. Great, I'm going to draw it. So, a water catchment, imagine it like a big bowl. Okay? And now what actually is a water catchment? Basically, it's like a bowl created with like mountains and hills and basically the terrain of the landscape, and how the water flows from the outskirts of the area into one waterway. So, for example, let's say my catchment's shaped like this. Okay? So this is obviously like, I don't know what this is, but basically if you imagine these to be like mountains, they're like peaks. Okay, maybe there might be some valleys in there where water comes in from another catchment. Actually, there might be a few of those inlets from other catchments. But basically imagine this like a big bowl. And what happens is you've got an outlet, so this is where all the water drains into another catchment. And there's going to be a main trunk, and that main trunk is fed by other streams that are flowing down from the mountains. Right, and those also have other streams, and those have other streams, and it basically just keeps going because the terrain is shaped in such a way. So this is basically what a catchment is. Now there's a lot of factors that change the shape of your hydrograph, and I'll get to those in a bit. And those factors are basically, the slope of the terrain, the shape of the outlet, so how narrow this point is or how flat it is also changes the size of water that exits at any one time. Okay, so converting rainfall to runoff. So a big thing in water resources is understanding the resources of water within a catchment. So that's what that means. So understanding how much water is flowing through the catchment, and we can actually calculate that from understanding how much rain fell at any one time. So if we understand the features of the catchment, so how much area we have and how deep our canals are and things like that, and then we also understand from a storm how much water fell, we can calculate the volume of water that's falling in the catchment at any one time. So this is basically what this part is talking us through. Okay, I ideally wanted to have converted this into a PowerPoint that's a little bit easier to understand, but I was really stuck at work today. So I'll just basically talk through what I wrote. So understanding the mechanisms which affect where the water comes from and how it enters the waterways. Wait, sorry, that just escaped my mind. Where it comes from and how it enters the waterways, how it doesn't enter the waterways is really important for this subject to make sense of it in your mind. Okay, so that's basically everything I just said. So understanding, for example, when water falls through, trees and rocks and makes puddles and stuff, that's going to affect how much water enters the river, and it's all those really minor things like that. So those things are called losses, which I'm going to get to now. How can you lose water? So water loss is basically accounting for the water that gets stuck on its way down the hill into the river. Now, the reason why I kind of screamed that in caps, this is really important concept, and make sure everyone is paying attention, because I don't know why it took me a really long time to understand how this works, because no one really dumbed it down for me. But basically, as water's falling through a catchment, it gets stuck along the way. I think I just said that 3 times. But basically, these are the 2 kinds of losses. So you've got continuing losses and you've got initial losses. Now, these are important because you're going to be needing to use them in calculations later on. So initial losses are things that happen very much at the start of the storm. And they're basically how water gets stuck in puddles, how it gets absorbed by mosses and the grass and the bark of trees, and how it gets caught in leaves and things like that. So this is think of this like it's a capacity of a sponge. So even though the catchment looks like this, it's not like a concrete pathway where the water just flows into the river and leaves. It's more like a sponge where the catchment itself is going to absorb water. Now the continuing losses, if we go back to soils, it's how much water the soil is going to absorb. And the reason why this is a continuing loss is because it takes a really long time for water to seep into the soil, as we already know, right? So really in a question, initial losses are going to be much higher than continuing losses. So for example, initial loss, in the first hour, you're going to subtract 10 millimeters from the rainfall measurement. Continuing loss is probably going to be more like 3 millimeters per hour after that. Okay, this is me just reminding myself to ask if everyone's done soil mechanics. Yeah, so can anyone explain to me why initial losses stop after the first however many hours? Okay, you can read it, but if you want to explain it to me in your own words. What do you reckon? Why do initial losses stop? So if we think about the amount, what the initial losses are, so divots in the ground, roots of trees, why does that stop eventually? Yeah, it reaches capacity. So like I read, you can only fill up so many puddles. If all the puddles are filled, the catchment's going to stop absorbing the water. So that's why the water's just going to flow off the puddles. Okay, rainfall losses. So the calculation part of this topic is really important in week 3, and it's basically what it's all comes down to. So these are just some diagrams I've chucked in just to visualize it further. So for example, if we look at the Haito graph, it's gone now. But the millimeters of rainfall at every period throughout the storm, think of it like that. There's a portion of it that you're just going to remove. Because that's not going to, this part is not going to enter the waterway, and it's not going to contribute to the hydrograph or the flood. Okay, this is another diagram which shows where the losses are. So for example, canopy interception, or just the terrain itself has puddles. Okay, so here's an example. So let's give this a go. So if we've got an initial loss of 6 mils, and a continuing loss of 1 mil per hour, can you tell me what the excess rainfall is going to look like? So excess rainfall meaning what's left over after the losses occur. So first hour, nothing happens, so we skip to the second hour. What's here? So initial loss is 6 mils. So what should be here? 4, cool. Now does that 6 mil keep going, or does it stop? Stops. Cool. So now we get continuing loss. So what goes here now? 4, 7, 3, 9, 3. Cool. It's actually really easy. It's not that bad. I think I'm being a little bit too passionate right now. Everyone's kind of scared to talk. Sorry guys. Okay. I hope this is not how my high school kids feel when I'm teaching them. Because I get more passionate when I'm talking about science and stuff.
Is that right?
Yeah, did everyone kind of get losses? Okay. Okay, this part's going to be a little bit more dense. Okay, so the phi index. So just ignore what's happening on the screen. I'm going to try and talk through it to sort of make sense of it before we actually get into the Excel spreadsheet where I've done a question. So basically the phi index is your continuing loss. And a lot of the time we don't know what that is. Why? Because we can't go into the catchment and count the volume of every puddle, or how many leaves are on the ground, or how many trees we have and how much water the trees can absorb, right? So we have to calculate, or we have to make an assumption of like what that is. And there's a few steps to understanding what the phi index is. So these are like the steps. Don't read those. I'll actually go through a question. So okay. Okay, here we've got a storm. So I know there's a lot of numbers going on, and I should have color coded it, but I didn't because my brain doesn't really work that way. So this is the timestamps of our storm. So the storm is happening, or at least we're accounting for the storm in 30-minute increments. Okay, this is our Haito graph data. So in the first half an hour, we saw an average of 4 millimeters. In the second period of half an hour, it was 7, and then 34 fell in the third half an hour and so on. And this is where the rain stopped. So the storm started at 8:30 and it finished at 11:30 p.m. Okay. This is now our stream flow. So stream flow, this is now our hydrograph. So this is the amount of flow that's occurring in our waterways as a result of the storm. So I might quickly put together a graph so you can actually see what this looks like. But if you look to this cell here, this is our peak. And when is our peak? It's at the end of the storm, right? Because no more water is falling into the catchment, no more water is draining from the catchment anymore. Obviously, it gradually decreases because it takes a while for the water to seep through the soil and the leaves and all that. But that's basically what's happening here. So our base flow, this is just like accounting for how much water is remaining like default in the river. Obviously, it's going to change because of infiltration from the soil, but don't worry about that. And then the direct runoff. So this is, I think I wrote that there. Yeah, so it's base flow minus stream flow. So it's basically just minusing off that. It's minusing off that little strip at the bottom that I was talking about before. And the reason we do that is because the base flow doesn't really account for the flood. The base flow is already there. It's kind of like, whether I'm walking on ground which is a meter higher or a meter lower, like I'm still walking on the ground. It's just my datum has changed. Anyway. Okay, now our volume. So the volume is calculated by multiplying this stream flow, so meters cubed per second, and then multiplying it by 30 minutes to get the total amount of water that has flowed through the river cross-section at that point. So, yeah, so that's basically just the sum. So for example, this amount of water fell in this half an hour, this amount of water fell in that half an hour. And I'm going to get a total volume of water that's flowing through the river just as a result of that storm. Okay. So, okay, this is getting a bit dense. I don't know if I should go through in like this much detail because I'm just going to bore everyone. But basically, if you just do all that maths and then you're going to get the the CQS. Let's go back to my notes just to see what that is again. So the CQS is basically the depth of the average depth of the water that occurred. So, okay. So let's say we've got a catchment, and this catchment is 18 kilometers squared. Okay. So if we have in total, where's my Excel? Okay, so if we had like this much volume of water and we spread it out across 18 kilometers squared, and then we divide it by that area, we're going to get the depth of water. So that's what that number basically is here, this QCS. So now from knowing that number, we can actually estimate our phi. So what this is we're saying, well, knowing this number, can we now estimate how much losses we had? Okay, so just a little bit more number crunching. Basically, you're just comparing this number to this number, CPE. So if we go back to my notes, CPE is the sum of all time steps. So it's like the sum of all the rainfall that has fallen if I just use my values instead of the actual values. And then at some point you're going to reach a value where CP is equal to QCS. This will make a lot more sense when you're doing it yourself, but this is basically what your typical question will look like in this subject. It's actually not that bad. I did this very quickly on the train, and I haven't done this subject in a year. So if I can do it, and I couldn't even do it back then, everyone in this room can most definitely do it. Trust me, I'm not the brightest person here. Okay, so no more numbers. I've tried really hard to not do numbers, but I thought it would be important to show you guys what the numbers might look like. I hope that wasn't scary, because I promise it's not. So now we're just going to talk about more like visualizing things. So I was hoping to just use, like at the end of explaining that question, I was going to explain how our guesses look in terms of like graphing. So this is like accounting for like the error, but anyways, so scratch that. Do we want to take a break? Or are we all good to keep going? Keep going? Cool, okay. So base flow recharge. So base flow. So as I said, the base flow is the amount of water that's flowing through the stream. Recharge, what does recharge mean?
Refilling the water.
Refilling it. Okay, so soil mechanics. How fast does water flow through soil? Fast or slow? Give me like a qualitative. It's very slow, right? So let's say we had, like this is like the cross section of like a river situation. Let's say this is the water level. And let's say this is the groundwater level, you know, before the rainfall event. Now, as a result of water infiltration, so that continuing loss I was talking about, let's say now the groundwater increases to this height. So now we've got all of this is groundwater. So your recharge is going to be all of this water seeping into the waterway. And so what's going to happen to the waterway? It's going to fill up, right? So in contrast to that, if we had groundwater that was lower, you're going to have, you know, an egress of water, so water coming out. So that's basically just base flow recharge. And so here I was going to explain how, like, when you have a hyetograph, like when I was explaining my example before, how the line wasn't straight, that's why the water, the line sort of peaks a little, you know. And like there's ways to like estimate that, but we won't really talk too much about that. Okay, this is basically just what I was explaining there. So the flow of water throughout the soil. Okay, this topic's pretty cool, and I would have hoped to talk less about numbers so you guys were like a little bit more keen still. Okay, so effective catchment shape. So this is like what I was talking about before, where the shape of the catchment will affect how the hydrograph will look. Can anyone talk me through this? Does anyone want to go like talking me through this? So how does the shape of the outlet affect how the hydrograph looks? Anyone? Spit words, doesn't need to sound good.
So based on like where it's coming in, as like narrow and then it gets wide, and then that affects the hydrograph.
Well, yeah, so if you think of this like think of it like kind of like a shovel, right? Or like a spout of like a thing. If you're pouring water out of something that's got a very big opening, it's just going to all come out on time, right? Whereas if it was constricted, it's going to be delayed. It's going to spray out kind of like a hose. And then if it was changing, you're going to have like different peaks, right? So you're going to have one peak for all the water that flowed out through there. And because there's like kind of like two outlets, it takes a while for all that water to get into this catchment and all that water to get out second time. So that's how the shape is affected. Okay, slope. So this is another factor I was talking about before, where the slope of the catchment will change. This one's a little bit more straightforward, because if you had a really high slope, obviously the water is going to come down at a much higher velocity, as opposed to like a shorter slope, which is going to sort of like trickle down a lot slower, and you're going to get a lower peak because, you know, the water's not coming down as aggressively. Okay, drainage density. So if we look at catchment I've drawn, so the difference between the two is that you have more lower, what's the word for it? Hierarchical waterways, lecturers. Anyway, so in this one they've got basically one main trunk and then one smaller stream coming off it, and that's going to affect it because the water's not going to be coming down as effectively. Whereas with more waterways, you're going to have more water coming out more effectively. It's not going to be intercepted as much. It's going to be flowing straight through the mountains and then exiting much faster. So that's how the density of drainage waterways affects it. Okay, land use. So this one's more like a built environment kind of thing, where if you have a highly urbanized catchment, well, I don't really need to explain that because you can see it, but can someone give me give me a reason why this might occur? Like, why might we see Sydney Harbour increase in water infiltration much faster than, for example, if we went out to Mudgee and you had like a mountainous catchment in Mudgee? What's the difference?
Also, this is like grams of water.
Grams of water. Exactly. So there's no interception, right? And in fact, this is what we want. So engineers that work in water resources and that work in treatment and bulk water, they want to drain the city as fast as they can because we don't want flooding in our cities. That's bad. That's not a good look. So we're going to have stormwater grates and pits, and we're going to have water mains that carry stormwater out of the city as fast as we can. Whereas a rural catchment is going to want to hold water. Why would a rural catchment want to hold the water? It's rural. Why do they want to hold it? They want to water their crops. Okay, so that's basically that. And I think that was the end of week 3. Okay, so in summary, can someone summarize what week 3 is about? So if we look at what Akshara taught us about the hydrological cycle and how that changes, what's the difference between her week and my week? How does the subject kind of pick up after that? Killed everyone.
It's like graphs and stuff.
Hey?
It's like all graphs.
Yeah, it's more graphs, but this is now starting to pick up in terms of what does water resources really need. So water resources is understanding how water is moving through our catchments and what is the effect of the storm and the information we can gather from that. So we want to know what is the shape of our catchment, where's the water going to go, how much water is going to be there when the storm comes.
I have another way that you might like to put it, right? So remember when I was talking about like evaporation measurement, how we were talking about like sticking an evaporation pan and kind of using it to estimate an area of evaporation? Like more often than not, 100% of the time, your catchment area is not going to be like a flat ground, right? Like there's going to be like hills, like Johnny said, there's going to be catchments, there's going to be vegetation there. And every part of like whatever ecosystem you're looking at is going to affect the way the evaporation occurs. So this is kind of delving a little bit more into that.
Yeah, basically. Yeah, so these are the different factors that affect how the water cycle changes from catchment to catchment. Okay, I've got really good news. Week 4, there's nothing in it. The reason for that is because week 4 is terrifying. I did read over the content, I promise. I didn't just do this because I'm lazy. I just think there's no point in going through it now when you guys are just going to study it anyway, and like I can already tell that like Irene wants to go to bed. So like I'm not going to keep going. But basically these are like the important points I grabbed from week 4. You can tell there's only a small amount of points because that's how numbers heavy this week is. Trust me, it's not even that bad. I was just a sloop when I did it, but I ended up understanding it. So, I'll zoom in. Sorry, that's a bit small. So, AEP, so the annual exceedance probability. So, what this acronym means, it's basically the likelihood of that storm or that kind of storm, like the likelihood that that kind of storm is going to occur. And so usually when we talk about an AEP, it's talking about the severity of the storm and how much water is going to fall. So for example, a 0.01 AEP means that there is a 1% chance that kind of flood is going to occur, or it's a 1 in 100 year type event. Okay? The ARI, so the average recurrence interval, is it's correlated. There's a correlation there, so it's got an inverted correlation, and that's basically it. That's it. I've got a nice little diagram here, which is really pretty and kind of explains how, or it depicts how the water level is going to change as a result of these floods. So, if you guys have heard of a floodplain, does anyone know what a floodplain is? So, a floodplain is like an area of land that isn't currently covered in water, but if a flood was going to occur, we know that the water is going to go to this area. So, we know this from surveying and stuff like that, or we know where how much rain there is. Basically, this is kind of self-explanatory. Like, obviously, if you have 100 floods, it's going to be a lot of water, right? So it's going to rise to there, as opposed to like a normal base flow is just down there. Okay, that's basically rigs 3 and 4. Thanks for listening. Does anyone have any questions at all? All good? Yes?
With the base flow, can it trend downwards or does it only ever go diagonally backwards?
As like after a storm?
Yeah, afterwards.
So, in my opinion, like I'm sure maybe there might be a circumstance where it might go down. I don't want to say no, but like logically, if you think about water falling from the sky and then it's being held in the catchment, the base flow will probably only ever go up a little bit and then fall because you're adding water to the stream. Whereas if you have a drought, that's probably where the base flow is going to fall because there's not enough water. There's no water in the storage of the catchment. Cool.
Anyone got other questions? Or otherwise, thank you, Johnny. Everyone can
Yeah. Thank you. Fuck yeah. All right. Cool. Thank you. And yeah, can I just add something at the very end here?
Yes.
So this was weeks 1 to 4, right? Actually, I did week 1 and 2. Johnny did 3 and 4. This first half of the course, there's a bit more, is more or less about like rainfall and designing catchments based on the probability of rainfall, right? The second half of the course is about groundwater, right? And
manipulating all of this,
Yes.
manipulating all the information, knowing that.
So you need the first half of the second half, and yeah, it'll have some soil mechanics because it's to do with like the seepage of water through groundwater. It's okay. That part's not actually as bad as it sounds. Yeah.
Can I just say closing comments? This subject's a bit of a yawn, but I work in water engineering right now, and I can tell you everything I learned in this subject is really useful. Understanding catchments, not only working in water resources, like water resources and water are two completely different things. I work in water and wastewater, but in wastewater there's a lot of man-made catchments. So draining water from suburbs and draining wastewater from suburbs, and how we can design a catchment which is optimum. So you're gonna like the outcome of the course.
Thanks everyone. All right, cool. Woo.